you need.
Okay, so I'm going to introduce someone who I hope doesn't actually need any introduction, but I'm going to introduce him anyway. So our speaker, Ves, did his PhD at Cornell with third party. He worked on opinion mining and information extraction. And then he first came to Johns Hopkins a few years ago as a Computing Innovations Fellow. And he has continued to work here at the Center of Excellence. And so since he's been at Hopkins, Ves has done some, I think, really, really excellent work in approximate inference for machine learning, which I think he's going to tell us about. And this is really nice work because I think it's one of the few occasions where you see work in machine learning that is both elegant and theoretically sound and also really, really effective in practice. And so I think he's going to tell us about that. He's also, while he's been at the Center of Excellence, he has been helping rebuild our entity linking system, and I believe that we've got really, really good results that are being presented in the talk. Is that today?
Yeah, yesterday and today.
Yesterday and today, and so this talk is also a little bit of a going away party for Ves, because he's actually leaving us in a couple of months, and so I thought it would be nice for him, as sort of a retrospective, to give us a talk and tell us what he's been doing. And so he'll always know what the rest of you are doing because he's going to Facebook. So I will give that up to us.
That's right. So thanks, Adam. It's good to be at this great institution. I heard it's especially renowned for its postdoctoral program. Very strong postdoctoral fellows coming out of here. But all joke aside, it's kind of strange to be providing the entertainment today. At the same time, I think it's a great opportunity to tell you a little bit more about the things that we've been doing here with Jason that I think are of interest, and hopefully there'll be some interest of people carrying out the torch once I move away. Oh, and before we proceed, today is an important day, so if you haven't done so, I encourage you to go exercise your right to vote and determine the way that this country is going. Okay, so today's talk will be about structure prediction. And structure prediction is all over us. It's in natural language processing, in social network analysis, in computer vision, and so on. But you still might not be sold on it. You may say, hey, it's nice, but in NLP, we really don't care that much about structure prediction. Well, let me give you one motivating example. So in NLP, we love pipelines. So say we start processing a sentence like Ford named Mark Fields its new chief operating officer. It's very typical that we run several components on it. So say we may first tokenizer, then part of speech tag it, then parse it. And then we may run something like a named entity extractor to see what are the named entities. Then we may run a relation extractor or something else. And then we have some application in mind. So our application will take in all this information. We will train some machine learning components typically, and we'll try to do predictions. And this is great. I think this is really good because in our day and age we have seen so much progress that we have very good tokenizers and part of speech taggers and parsers as something that wasn't around just 10 years ago. Oh, okay, maybe I shouldn't say that. But at the same time, there is a bit of a problem in this because we take these components, they've been trained on some specific data. More often than not, your parser, named entity tagger, even your part of speech tagger will be trained on the Wall Street Journal. They work great on the Wall Street Journal. You get 95% accuracy, but then you go and you run it on New York Times, and the style is different, so your parser fails miserably. And then if you want to run it on something even more something informal, then you really are running into big problems. So when you deal with the NLP pipelines and you rely on multiple components that are trained out of domain, And you really, what you care is the end test that you're performing. So you really care about the performance on your end test. And you really don't care what happens in these intermediate steps. For you, there's some sort of a latent representation. But the errors propagate, and you want to be able to have components that don't do the errors that will propagate and you hurt your end task. So this is why you can think of an NLP pipeline as a structured prediction task. So I think that's not so much that something wrong with the way that we're doing things right now, but I think there's more of an opportunity to improve things by treating the entire pipeline and all the intermediate phases as some sort of latent representation, and then tune the entire pipeline to do well on the task that you're interested in. And certainly people have attempted to do that. So there was a paper by Finkel and Manning doing joint parsing and named entity tagging. And I think a very interesting paper came out in this year's GMNOP by Narodowski, Radel, and Smith, in which they said, parsing is really just latent to us. We really care about relation extraction. So let's just marginalize it out and train in a way that we improve our... This is David Smith. So how can we do joint classification in this case? Well, we have these beautiful formalisms of probabilistic graphical models, such as Markov Random Fields. So I'll be talking a lot about Markov Random Fields today. And what's nice about them is that they provide you a nice principal way of combining the different components and talking about joint distributions. Also, they give you ways to incorporate your prior beliefs about the data that you're working with. So here's another example. This is a problem that I'm very interested in. This is social network analysis. So say somehow we've gotten our hands on this network of people and their relations, and we want to make predictions about the participants in this social network. So maybe we can guess the gender based on the name. We can do probably pretty well. Then we might have a set of documents associated with each of these participants. So for example, this guy, Peter Smith, tweeted, "I'm so happy that Obama won." So we will label him as a liberal right away. And maybe, someone else tweeted, maybe his father tweeted, "Oh, Peter and I are going to Mass to celebrate Easter," so we guess that he's a Catholic. So we can guess about the attributes of the network for which we have some observation. And then we want to fill in the remaining attributes given this network structure. So we know that this attribute, so for example, if someone is American, we know that their son is likely to be American as well. So we have some way of doing educated guesses. And again, this is a structured prediction problem. We can express this network as a Markov random field. And again, this gives us these nice advantages that we can do it in a principled way. So great, let's then use structured prediction for all these problems. What's the problem? Well, so there are at least two issues that make structured prediction ineffective that I'll be talking about today. So the first is the use of approximations. So if we go back to this NLP pipeline, we said we want to sort of marginalize out this hidden structure. If we want to do this effectively, we shouldn't really rely on the one best output of each component. We should rely on some sort of a distribution. And if you notice, I only draw the part of speech tags here because if I wanted to draw the distribution over parses, this slide will be really, really messy. And the point is not only that the slide will be messy, but if we want to compute this distribution, even though we can compute each individual distribution exactly, we cannot compute the joint distributions. And that's due to the fact that usually we assume some sort of sequential dependency between the part of each tags. And then we have these dependencies that propagate along the trees when we deal with the parsers. So you can see that these things will form loops. Once we have loops, we can use our traditional dynamic programming algorithms because we have nowhere to start from. So that's why we need to use approximate inference. The same goes in the case of our social network prediction. Say we wanted to predict these particular attributes. We can look at the attributes on which this will be depending. So we depend on its immediate neighbors of the social network. But if you notice that some of those attributes are also unknown. So we can, and when we try to predict those, we would want to rely on that attribute that we're predicting. So we have this chicken and an egg problem, and that causes us to not be able to do exact inference. So approximations, and I show you one kind of approximation, that's approximation to inference. There's also the process of decoding, which means that we've computed a distribution, we want to produce a prediction. And there we also may have to rely on approximations in some cases. Also, the structures of these models are really an approximation. So I think in NLP we no longer believe that natural language has a context-free grammar structure, if we ever did. And the second problem that I will be talking about today is the case of limited data. So in these social networks that I showed you, we often have a single example. We want to utilize this example both for training, acquiring model parameters, and also we'll be using it for testing. And that sort of goes against the traditional machine learning assumption that you have i.i.d. samples of data. Just in 2 sentences, the idea of our work is that we want to train fast discriminative models that work well under the expected data distribution. So this will include 2 advances. One is training by minimizing the risk of the entire system. The second one is using data imputation for learning in the limited data setting. So in the remainder of the talk, I'll give you a really brief overview of Markov Random Fields. I think almost all of you, or pretty much everybody here knows what those are, but just so we have common notation. Then I'll tell you about our algorithm for learning parameters of Markov Random Fields through empirical risk minimization. And then I'll talk about the data imputation issues. So what are these MRFs? So MRF is sort of a combination of probability theory and graph theory. It's a formalism for expressing joint distributions of sets of random variables. And the nice part here is that we can draw explicitly the model and the dependencies we factor along these black boxes, which we call factors. So then we can use this explicit structure to use standard inference algorithms that take advantage of the conditional independencies. And you will also hear me talking about conditional random fields. So those are just like Markov random fields, except for we'll always given the values of some of the random variables. And that means that we don't have to model the connection between the input random variables. So we have less parameters, and usually in practice that leads to more accurate models. And this will be the only slide with math in this talk today, I promise. And this is really not so much to show you what the math is, but to give you an idea of how the distributions of these MRFs are defined. So we see that for a particular configuration, we have features that are associated with these factors. And then for each feature, we have a corresponding weight. So really the point here is that what I'll be talking about learning today is the weights of these features. So today's talk will be about learning in Markov Random Fields. Right. So actually this notation is a bit inexact because you can have multiple features over each factor. Oh, I guess f phi I. Right,
so
that's right.
For example, when you have phi3, you can have phi3 and phi3.
Right.
The I indexing the factors and phi I tells you which variables are involved.
Why phi I is the
It's the subset of variables involved.
right. Okay, so we talk about learning today. So typical learning setting, we're given some data. Those are sets of random variables, and we want to learn a parameter vector that minimizes or maximizes some objective. And really the first part of the talk today will be about what objective we're minimizing. So this is where we'll talk about our ARMA algorithm. So traditionally, when you train a graphical model, you do something known as maximum likelihood estimation. So the idea here is you want to pick the parameters that maximize the likelihood of the training data. You can do that. There is no closed form solution, but if you run inference repeatably, you can sort of scale down this convex function. So maximum likelihood estimation is actually really nice, has very nice properties. It's convex, it's consistent, which means that in the limit of infinite data, you'll recover the parameters of the true model that generated the data. And it's also asymptotically optimal. As more and more data becomes available, you recover the true parameters at an asymptotically optimal rate. Right, but what happens when we use MRFs with approximations? So this is what happens in practice. We build these beautiful systems that have an MRF at their core. We have a very principled way of building them. Everything makes sense and it's beautiful. And then we add, then we cannot run exact inference on the system. So we add approximations. And what we so I mentioned we have to approximate the inference, the decoding, the model structure is misspecified. And the fact that we're training for a single set of parameters in itself is an approximation. So what we end up is really a big computational hack. It's some computational function that reads inputs and produces outputs. It has great motivation. But it really doesn't do what it was meant to do because we're using it with approximations. So should we still be maximizing the data likelihood in this case? Well, this is a rhetorical question. I'll try to argue that we shouldn't. So what we should do instead is this idea of end-to-end learning. So let's do this. Let's match the training and test conditions. And let's pick the parameters that minimize our loss of the entire system on the training data. So intuitively, that's something that should work well, right? It's also known as empirical risk minimization in machine learning. So certainly this should sound like a good idea, and people should have done it by now, right? What's the catch here? Well, the catch is that it's not really trivial to minimize the risk. But we can do it using this error back-propagation algorithm that people have used in neural networks for many, many years. So how does that work? We use back-propagation to compute gradients with respect to the output loss. Then we plug these gradients in a local optimizer to find the parameters that minimize the training loss. So if we look at the optimization criteria that we want to choose, we want to choose a criterion that's both approximation aware and loss aware. So we want to be here in the bottom right corner. So if we look at the maximum likelihood estimation, you could argue that it's approximation aware. Well, it is approximation aware. There's also have been methods that are loss aware, such as structure SVM, maximum margin Markov networks, and the softmax margin of Gimpo-Smith, which just came a couple of years ago. And our learning algorithm fills this void because it's both approximation and loss aware. So let me tell you how the algorithm works intuitively. So what we use in NERMA is this idea of backpropagation of error to do the empirical risk minimization. And backpropagation of error has been used to train neural networks for a very long time. So we can use this algorithm. This algorithm allows us to compute gradients of the output loss, and then we know how to minimize, find the parameters that minimize the loss using local optimization. So what people have done in neural networks is they have these neural networks. They forget about their structure. They say it's just a black box. We fit it some inputs. We get outputs that we want to. It's parameterized by some parameters theta. During training, it makes sense to train it to for the parameters that minimize the training loss. So if we gray out the black box, you see this used to be neural network. Well, we're saying we really like our Markov random fields and conditional random fields because they allow us to build in our intuitions about the data and the representations that we want. So instead of neural network now, we'll be training an MRF-based system or a CRF-based system, but we'll train it using the same principles as neural network. Okay, so what is this? Sorry, Scott? So there are issues with differentiability. Essentially, they have to be differentiable. And there's also issue of convexity. So many losses are not convex. So in practice, we have to do some tricks to deal with the non-convexity. So instead of giving you all the math, I'll give you a metaphor of how error backpropagation works. So say you're playing pool. You're trying to make the 13 ball down in the bottom left corner. And you have a single parameter, which is the angle at which you'll hit the cue ball. So you have a pretty good guess of how this may work. You take a name, you take a shot, and, well, you didn't make it. So how should you correct your stick angle? Well, gosh, this was a very complicated chain of events that led from you hitting the white ball to the 13th ball not making it. So you're kind of screwed, right? Well, no, because you remember the path that the balls took, and you know how to work your way backwards. So you can say, well, I wanted the 13 to go a little bit to the right, so I have to hit it a little bit to the left. So then I have to hit the 14 a little bit to the right. So I have to hit the white ball this way. And if you're a pool pro like Jason, you may argue that this is not physically feasible, but I'll let you figure out for yourself. So you take another aim, you take another shot, and well, you know, sometimes you have to iterate more than once to get these things right. So the point here is that error backpropagation works in much of the same way. So even though we have this complicated chain of events that leads from us feeding parameters to the model producing an output, each individual step is rather simple, and we know how to differentiate it. So, so in our case, you know, instead of hitting a ball, we're computing a message, or we're computing a probability. Instead of making a ball in a pocket, we're predicting some quantity. But the idea is the same. So more formally, the way that error backpropagation works is by applying the chain rule of differentiation over and over again. And we talk about forward and backward pass. So the forward pass is just, your vanilla inference in your model. And the backward pass is doing everything in the reverse and computing gradients. So just to show you schematically how it works, you may start with your parameters. You compute messages, say you're using loopy belief propagation. You keep updating your messages. Then you compute your beliefs. From the beliefs, you compute an output. Then you compare it to the true output, and you compute a loss. So this is your forward pass. The backward pass will be exactly the same, except for we'll do everything backwards, and we'll be computing gradients. So we compute the gradients of the loss with respect to the output, with respect to the beliefs. We keep iterating, computing gradients with respect to of the output loss with respect to messages. At the end, we have the quantity that we wanted. This is the gradient of the output loss with respect to the input parameters. So once we have these gradients, I think pretty much everybody here knows what to do once they have a gradient. They can use something like a stochastic gradient descent to find a local minimizer. Well, in practice, we found that it's better to use a second order method, such as stochastic meta descent. For that, we need some more automatic differentiation magic to compute vector Hessian products. But the point is that for both the gradient and the vector Hessian computation, really we don't pay much in terms of efficiency. So we pay a small constant. In our case, it's something like 2 or 3 times the cost for the forward pass. Okay, so this is the algorithm. Jason?
So for people who might want to do something else besides optimize this function, it's not just for our case, actually. It's cheap. I mean, this is cheap for
right. Right.
It's useful to know how to compute derivatives automatically and vector Hessian products automatically. You can always do it.
So this is one of these things that Jason says that everybody should know, and now that I've seen it, my eyes are open. I agree with him. So take one of Jason's classes. And
You're teaching it.
that's right. Okay, so let me try to convince you that this actually works in practice. Now that Adam set up the bar so high, I have to sort of show you that this really works, right? So we have an implementation of that in a Java package. It's available from my webpage, and you're welcome to use it. And if anybody has a problem that seems particularly interesting, I'll be here for another couple of months, so I'll be happy to try to get you started using this package. And the package is meant to be generic, so hopefully it will work easily for your problems. So for these experiments, we use CRFs with loopy belief propagation. More precisely, we're using something called sum product belief propagation, which is the loopy version of the forward-backward method. But results using a max product belief propagation, which is the loopy version of Viterbi, are the same. So I'll just show one results here. And we'll be optimizing accuracy and F1 score. So let's look at one application. So this is really social network analysis in a way. So here we want to model congressional votes. And the irony is that this example is very appropriate for a day like today, right? And that wasn't intended. In this case, we want to predict how each congressman voted. We have a transcript of the speeches that each congressman gave during a debate of a bill. And we also have the recorded vote of each congressman, which is either yes or no, or yay or nay. And there's also an additional source of information here, which is usually congressmen refer to each other in their speeches. And this could be either in agreement or disagreement. But the local context around each mention gives us strong clues of whether this is done in agreement or disagreement. So we can benefit from doing this prediction jointly. So this is what one of our examples in the training corpus looks like. So this is a CRF that we produced based on a single debate. And here you see 3 kinds of nodes. So the white ones are binary random variables. They're either yes or no, indicating how the congressman voted. They're conditioned on these dark gray nodes, which are corresponding to the text of each article. And we also have these 3-way factors that are conditioned on this light gray node. So this is when one congressman refers to another. We condition on the context around that reference and add this 3-way factor. So this is the results from the original paper trying to predict how each congressman voted. What they used in the paper was they trained one SVM model to predict yes or no and one SVM model to predict agreement or disagreement. And then they used the min-cut formulation to try to consolidate the scores of the 2 classifiers. So the point is the 2 classifiers are trained in isolation. When we go to a loopy CRF model, now we can talk about the joint probability of all the votes, and we can build our models. We can train our models jointly, so now we can trade off the weights for the agreement versus the weights for the yes and no. So when we go to a loopy CRF model, even when we train it with maximum likelihood, so just substituting approximate inference for exact inference, we see a big boost in performance. Then if we use a loss-aware method, such as the softmax margin of Gimple-Smith, we see further improvement. And when we train it with our IRMA algorithm, then we see a further boost in performance. So we did this for a NACO paper, and we tried 2 more NOP tasks. So I won't go into much detail of what these tasks are. So one is semi-structured information extraction using a skip chain CRF. And the third is multi-label, collective multi-label classification. But the point is, for all 3 tasks, we saw the same pattern. So going from a non-loopy baseline to a loopy model trained with maximum likelihood, even though it requires approximate inference, our results improve. And when we train this model using our IRMA algorithm, we see further improvements. So we have in the paper. So basically, here you also see a slight improvement over the maximum likelihood, and for the 3rd task, you saw them actually do a little bit worse. Right. And if that didn't convince you, in the original AI stats paper, we experimented with synthetic data, and we saw the same results, that our method improved. And if that didn't convince you, there's more. So this is, we applied the same learning algorithm to the task of entity linking. So at the COE, as Adam mentioned, I've been working on entity linking. And we built the system called KILL. So when we train KILL using maximum likelihood, this is the accuracy that we get. If we train it with IRMA, we see an improvement. And if we add another machine learning trick called structure prediction cascade and train it with IRMA, then we see an improvement of more than 2 accuracy points. And as Adam mentioned, these results were presented yesterday at the tech workshop. So our system came in 2nd out of 28 participants in the English entity linking task, and it's using this technology. Okay, so hopefully I've convinced you. I don't have any more results here. Just to sort of summarize this part of the talk. So I showed you our learning algorithm to risk minimization, and it leads to surprisingly large improvements on 4 problems, improving over the state of the art. And I also want to emphasize again that you should try to use IRMA for your problem if it makes sense. Don't be afraid of having to use approximate inference. You can use our learning algorithm and do better than the simple model without need for approximations.
So did you say surprisingly large gains? Do you mean like we're surprised as an audience that they're so large, or you were surprised?
Well, of course I knew that the gains would be achieved, right? No, that's surprisingly for you. No.
So Wes, you're saying use IRMA. So in addition to the training data, the XY labels, and the black box that computes the loss, what else would I have to give yourself?
So you would actually have to. So you will have to have your loss sort of work with the rest of the system, so propagate the gradients through it.
You would need the black box should also give me the gradient of the loss.
Right. So you could either use one of our losses or implement your own loss in IRMA, so it would pass backwards the gradient. Or if, yeah. So that will be what you need to do, and then you could provide your training data. We have a format for describing general MRFs, so you can.
So there is a bit more work. In other words, in addition to specifying the model, you also have to find the loss. Like the model is straightforward. It's an undirected graphical model. Specify one. The loss is typically the tricky one. It's something given to you by somebody, and then you have to compute these gradients of the loss.
Right.
And that is external to the software.
So far the gradients are internal in the software, and we have implementations of sort of the regular loss functions like accuracy and F1 score. If you have a more sophisticated loss function, like word error rate or something, you would have to either implement it inside of our software and implement the differentiation of it, or you would have to decode the outputs yourself and provide the gradient back into the training method. So there'll be more, and of course you probably have some interesting decoding algorithm that you would have to implement and sort of differentiate backwards as well. All right, so that was about IRMA. I had about IRMA. Then I'll talk a little bit about this issue of data imputation. So this is current and ongoing work here that we're doing with Jason. Hopefully we'll get a lot of it done before I leave, and we'll have someone take over. So if you're a student and looking for a project, we're interested in hearing back. So Jason likes to call this IRMA for imputed risk minimization under approximation, and I guess it's kind of starting to grow on me, so that's why I put it on I added it to the slide. So what's the issue here? Say we had this one large example that we wanted to predict attributes about. So this is in the social network analysis case, and more generally it happens in structured relational learning, for those of you that are familiar with the lingo. So we have one example, and we want to both train and test on it. So how do we do it? And in general, this is just one of the cases that we're considering. We also consider cases in which we may have limited output. So when what I mean by that is usually expensive to get supervisory information. So you have to, you can benefit from some sort of a semi-supervised learning. And also you may have limited inputs as well. So we would like to still be able to use our discriminative models to learn these computational hacks that give us good test time performance and are fast. But we still would like to incorporate our intuitions about the data. So we have some prior beliefs. In many cases, we have to bias the learning process in some way to be able to do predictions in some sensible way. So here comes Bayesian decision theory to to the rescue. So we want to learn using this sort of Bayesian formula, which says that we should pick the parameters theta star that minimize the loss of our decision function under the data distribution P of xy. So in a little more detail, we have the parameters that we want to learn, the optimal parameters. We have some loss that's usually task specific. That's the loss that we'll be evaluating our system in, so that's why we want to minimize it. This is our decision rule. So this is the fast discriminative decision rule, the computational hack that we're training. We want to minimize the loss of this in this data under this distribution P of xy. So this is the data distribution, and when we talk about imputation, is really talking about where this data distribution comes from. So Jason also likes to call this the science and the engineering part. So this is what we want to engineer, a fast decision rule that we use during testing. And the science is the data distribution, where we put all of our intuitions about the data. And we can, and usually computing these data distributions is difficult, it's time consuming. That's why we only want to do it during training time. And you can also think of it generative versus discriminative. So engineering is the discriminative part, and the science is the generative part. Okay, so the big question here is, where does this distribution P of xy come from? So what we want to do in this work is to utilize data imputation. So we could do two things. We could complete missing data, or we can censor existing data. Or actually, we could do a third thing, which it's not on the slide, which is completely hallucinate data that's not there. So let me motivate this with the SRO setting. So we wanted to train here. We had some partial observations of this network. Well, one way to train a fast discriminative rule is to forget some of the attributes. Like, we forget this guy's nationality, and we learn how to predict it given the rest of the network. Another thing we can do is that pretend that we know, so impute some of the data, pretend that we know this nationality, learn to predict it. So the big questions that we're trying to answer here currently is, how do we complete the data and how do we censor the data? And the idea is that we want our training time distribution to be close to what we see at test time, so that our system will be accurate on this distribution. So two things that we are developing. So we need a censorship model. When we hide data, we want to make sure that we hide it plausibly. So for example, if the nationality and religion are always missing together, or are present together, and if we're not careful, we may learn to predict nationality very well from religion. Then when we go to our test data, this will never happen, so we learn a rule that's essentially useless. We also need to be able to model the distribution over the queries. So if the questions that are asked are always, say, 3 hops away from the observed evidence, we want to see that during training as well. We don't want to train on predicting values that are 1 hop away from the observations. So we've been so this is still ongoing work. We're developing these models that we're using for imputation. So this was, the SRO was one setting in which I wanted to motivate this. Another one is training with limited data. So this is more akin of the traditional semi-supervised setting. So say we have only a few outputs but many inputs. Well, we can use this trick called uptraining. So we can train our simple, fast, discriminative model using data that we impute from a more complicated but slower model that we use only during testing. So this has been done in training a single classifier for ensembles, training local classifiers from output of a PCFG or CRF, and actually our own area, Mark and Sanjeev have worked on, have proposed an approach like this. So this is in a way of, for us would be a way of utilizing generative information in a discriminative classifier. You can try to doing the converse, so maybe you have many inputs and you want to input the, you have many outputs and you want to input the inputs. This is a work that Jifei did with Jason and Sanjeev. So here maybe you're doing machine translation, you have sentences in Chinese. You want to impute the sentences in English and then train the English to Chinese translation system. And so how does this relate to our NLP pipelines, you may ask? So here, again, we may want to do the more principal generative thing when we are training our pipeline on the end task. So we had this end task in mind. We could generate training data and train the whole pipeline using fast discriminative rules that during test time we don't really want to compute this whole mess that is here. So I think this is basically just to wrap up the data imputation setting. So we're interested in performing discriminative training both in the case of semi-supervised data as well as the single training and test example in the SRL setting. And we're working on modeling the mechanisms that create the data. And this is I included some of the past work that I've done so people would be aware. So one thing that I think that might be of particular interest to people here is that together with few other people organizing on a semi-val task on Twitter sentiment analysis. So this might be something of interest. Teresa is also involved in it. We also have a reference resolution platform that's available for both to train your reference resolution algorithms as well as a reference resolver. And I'm now working on this entity linking and knowledge-based population tasks. So now is your time to exercise your right to ask a question in the symposium, so please feel free. There was some early questioning, right?
I want you to spend a few minutes on this automatic gradient computation, but if there are other questions, let's answer this first. No, because this is a very, I guess it's a detailed question.
Uh-huh.
We can talk later other than other questions.
Adam?
The imputed data part. Is the problem that, are you considering the case where you expect the distribution over missing and non-missing data to be different at test time from what you have available at training time? Is it possible to learn from your training data what data will be missing? Or are you considering the case where maybe everything is observed at training time, but there will be something missing at this time, just not?
So regarding the missingness part, we think that we can learn from so we think that we can learn the missingness pattern from the training data. So essentially what we're thinking of utilizing is essentially MRF with binary MRF that has Boolean yes or no, missing or no random variables, and at least that's always given in your training data. You know if a variable is observed or not.
So you expect that condition of missingness to also be matched in this.
Right. We expect that. Whether or not that will hold, that's a different question. Travis, did you?
Well, yeah, kind of follow up on that is the idea that you only need the MRF to model the missing data, but once you have an estimate of missing, then you can train it past the CRI.
Right, that's essentially. Well, it's not only that the model is necessarily simpler that we're training, but we also are not as concerned on being correct when computing the distribution. So we can learn, for example, the same MRF but with less, say, iterations of loopy-belief propagation, or maybe we can use more iterations of sampling during training. So it's not, doesn't mean that the model necessarily has to be simpler, but the computation will be less during testing.
I also have one other question with respect to approximate inference versus convexity of a lot likelihood. You said that maximum likelihood is always convex for MRF.
The exact likelihood is convex. And whether or not the approximate.
Like a complete data.
Yeah,
Right.
Assuming everything is observed. So when everything is observed,
For an MRF.
For MRF, if all the
And MRF is just an exponential model. It's a linear model.
Yeah, I'm saying, what does it mean for everything's observed?
so when you have that
Oh,
PDF y
I see.
equals
So then,
the
yes,
sum,
it's
take
trivially
out y,
convex then.
all the y's are observed.
Yeah, you don't even need to run any real inference. You can do local learning with everything.
No, you still have to fit.
no, you still have to.
It's not based on count because it's featureized, right? So you don't, the model is not in non-parametric mode. You still have to fit the parameter.
Think of linear chain CRF. You have to train it using inference. It's not a closed form solution.
When you're thinking about CRS, if something is hidden.
Right, exactly.
If you had no regularizer, you could just take
Right. The global normalization.
Is it any indication of your political affiliation that the element has only 3 stars
It was not intentional. Well, let's not get political. So I guess we probably have a minute or two to answer your question.
Yeah, give it a couple of minutes and people get bored and we can leave. I would like to get it.
So you want
I want to understand what you mean by saying automatic derivative computation. In what sense is it automatic?
so it's right. So
Because that seems like a key part of that work where you think.
So in theory, I mean not in theory, you could take your computational function and fit it through a compiler that gives you a program that computes the derivative of different quantities that you specify. The caveat is that if you do this automatically, usually you pay a price in runtime. So what we did instead is we write code to compute the derivatives of each individual function given its inputs and its intermediate quantities. So during the forward pass, we run our functions, we remember some intermediate quantities, and then during the backwards pass, we write a code that takes these intermediate quantities, for each step computes the derivatives. if you were to do this completely automatically, you would have to remember all the intermediate quantities, and in theory you would work, but in practice it's not quite as easy.
It's easy to do like a simple linear chain CRF and show me what you can buy.
You'll get the, if you have start with forward algorithm, you'll end up with backward algorithm when you differentiate.
Yeah, so you want me to show you how the derivative is computed, or?
No, I want to understand this notion of compiling the function and so that the derivative comes as part of the computation. I don't think I completely understand.
Right, so what I meant was you have a compiler that produces a function that's the equivalent of the forward function that computes a derivative.
Okay.
So, for example, you have a function that computes x plus y. Then you can run it through this compiler that will split out a function that takes the derivatives of y. So you had z equals x plus y. You will take the derivative of z. You will compute the derivatives of x and y. And it does that really. It's really that simple for each.
There's two related concepts here, actually. It might be worth using the terms automatic differentiation and algorithmic differentiation. Algorithmic differentiation is some mechanical process for taking a function which is computed by some kind of code, like maybe it has loops in it, and having code that computes the derivative of that function. One way to do this is you have a source-to-source transformation, where you start out with code in one language, and you get more code in the same language. So your first code is for F, and then you're going to get code for grad F. What the language that you pick makes this easier or harder. There's a system called Stalingrad for doing it in Lisp, for example. Sometimes you may end up taking more space than necessary, depending on how smart the system is in knowing about properties of commutativity and things like that, so that it knows how many. If you're computing if your loop is computing a sum of 100 things, then you have a number of partial sums along the way. And if the system isn't so smart, then it'll compute derivatives with respect to all the partial sums. But if it's smarter, it will know that the sum of 100, the derivative of the sum over 100 things, the sum over the derivatives, and it doesn't have to compute it doesn't have to remember the partial sums of the original piece. So you can be smarter or dumber about how to do this. It turns out it's quite nice and done.
This is algorithmic differentiation.
That's algorithmic differentiation. There's another set of technologies called automatic differentiation, which just keeps track of the intermediate quantities as the program runs in such a way that it can then replay backwards. It's basically keeping a trace of the program as it runs forward in such a way as it can then replay it backwards and compute the derivative.
Okay, so I was wrong. I told you could do it in compile time. You can also do it in runtime, right?
And there are toolkits for this also.
I guess that.
So basically, instead of using double in C++, you would use something special called a double. And a double is like a double, but it contains enough bookkeeping that when you multiply two a doubles to get another a double, and the operators are all overloaded, it'll remember how to propagate the derivatives backwards.
Okay. All right. And are you exploiting the exponential model for this, or
no? Not particularly. In fact, what Ves is doing here is
what
not
I'm thinking
either.
is, in general, this could be any black box net. You had a neural net earlier, right? It could be something like that. And you're saying that this particular technique of using automatic derivatives that you keep track of
intermediate quantity.
Intermediate variables would work even there.
Yes, but in fact, this is not a black box. And so what actually happened was Ves worked out the derivative of this particular algorithm by hand.
So yeah, so if
this algorithm being the IRMA algorithm.
Being the approximate CRF system. So the top half of this happens to be a particular algorithm when you're using, say, sum product belief propagation. And if you simulate what the automatic method would do in this particular case, then you can figure out what the code would have to be for the lower half of the slide. So this was actually not done automatically, but it was done following the recipe that the automatic system would use.
Right, but it's still called automatic differentiation, right? Even though it's done manually, because
Who knows? I think terminology varies depending on who you talk to. Certainly called back-propagation.
right.
And is automatic differentiation something that's already supported in some, you mentioned some
Yeah.
programming language, is it?
Well, you mean in a program like?
Or in some.
So actually, to be completely precise, we do use some really automatic differentiation. So when I said that we also compute the derivatives in a forward mode, so for that we used a package for Java that has overloaded operators and can compute derivatives in the forward mode. So when you do it in the forward mode, it's a little bit easier to do it because you can maintain the derivative quantities with you and you don't have to rerun computation backwards. The caveat is that you can compute the derivative only of a vector, pre-specified vector of input. So you cannot do it for the entire system, but you can do it for the vector Hessian products.
Right. And those overloaded objects that carry derivatives forward, if your original functions line is, if your original operators line is semi-ring, then the particular case of things that carry the derivatives forward is also a semi-ring, and that's the expectation semi-ring.
Right.
Yeah, so actually, now the connection is complete.
Great. All right, well, I think we should let people go vote now after all the motivation that I've given. So thank you.